Well, somebody said recently it was expensive to move everything over there, but maybe
Who said that?
Kevin.
Kevin who?
From downstairs.
Yeah, server Kevin.
Server Kevin.
Do you say it's expensive to move everything over there right now, and where everything is an entire rack?
I mean, it might have just been.
You can look up the prices online. They're, a rack costs $250 per month, I think, for the cheapest rack.
So it might be more expensive than we're paying now, given that it's
it's free right now.
Right.
$250 is more than
free.
Yeah, I think it also went down a lot in last year. They considered moving after the power craziness incident last year, and it was a lot, or at least the price they quoted to Salim at least was a lot more expensive than it is now. I think. Yeah. It's also a difference. I mean, I put 4 U's of computers over there, and the computers that the math department has taken together is like 20 or 30 U's. So they have a very large, they have a lot of different computers. I don't know why they have more than 2 computers, to be honest, but they have a lot of different computers. They probably should just have like 2 or 3. So yeah, there's a lot of different options for racks, and it's tempting to get the most expensive one, even if, and then try to compare the price between the most expensive rack facility you can get over there and like what we pay now. But you have to keep in mind, if you get the most expensive rack, you're getting way, way more than what we get now. Like, you're getting your own generator for that room. Like, they have one room that's on their own generator and one that isn't. And that makes a significant difference in price. So then you'd be tempted to go with that, because it's only $150 more a month. But on the other hand, we don't have a generator now, so it's tempting. Okay, so I'm going to start the talk with going over, so the first talk was an overview of the kind of economic, social, cultural, motivational background of Salvus. And the second part is about the technical aspects of specific technology components, so pieces of software that I've chosen in putting together Salvus. So an overview is, here's the stack. First there's infrastructure, which is built on top of hardware. So there's a private cloud, a whole bunch of virtual machines running in various locations on computers I control. And most of those computers have only one account on them, which is mine, so they're not used by anybody else. And then there's public clouds such as Google and Amazon and so on. There's a virtual private network, there's a database, there is SSL termination, there's load balancing, there's static HTTP serving, dynamic HTTP serving, math computation, and general management of all the components. And so that's what makes up the stack that is Salvus. And the picture that kind of illustrates this, you have a bunch of clients, they connect to S-tunnel processes. The connection here is SSL encrypted. Then the connection, everything here is unencrypted by the software itself, but it all runs over a private network which sits on public networks, and that private network has all traffic encrypted. So it's not the programs doing the encryption once you get down here, but the traffic is automatically encrypted by virtue of being on this other private network. So then you have all these load balancers, you have static web servers, dynamic web servers, VPNs in here holding it all together, and a bunch of Sage processes running. I don't know how the number of different components will be balanced out in the end over time. My intuition now is there'll probably be far more Sage servers than anything else, so that when I have to add capacity, mainly what I'll be doing is just starting a virtual machine somewhere and then running a bunch of Sage processes on them, because I'm guessing that that's going to be by far the most resource-intensive thing at this point. Since the problem of serving static content to very large numbers of users with a fairly small amount of resources is very well solved, I doubt that's going to be the bottleneck. The dynamic stuff with WebSockets is harder, but it's still pretty well solved, and you can handle quite a few users with one single tornado process. The problem of having 1,000 people at once, say, doing something with Sage, well, that's just going to take a while, just because if they're all doing something that's time-consuming, you really want to run that on a lot of different computers. But it could turn out I'm wrong, and that most people that use Sage will be impatient users that couldn't possibly wait for more than 1 second for an output, and hence anything longer than a second they'll end up killing. And in that case, much less usage of the sage servers would be required. It could also be, well, I mean, I just don't know. We'll see. But fortunately, things are set up dynamically enough that things can be changed. Also, I don't know how many databases will be required. That is, it's unclear how much I'll want to store and how redundant I'll want to make the storage. So first, the connection between the clients and the Tornado server uses a library called sock.js. This is a fairly recent JavaScript library that, there's a protocol called WebSocket where you take a standard HTTP 1.1 connection and you upgrade it to a persistent socket, so that now if you want to send 3 bytes to a person on either end of that connection, you just send 3 bytes. That's it. So it's completely different than what you have with HTTP, where every single transaction involves sending a header, which is several thousand bytes, along with the actual information. And it's a complete, you make a connection, you send that information, you terminate the connection. I mean, this happens every time. Like when you load a web page, typically your web browser will make potentially hundreds of connections to get all the content that's in that website, in that particular web page, if there's lots and lots of different URLs in there. Every single bit of that content is a complete connection to grab it and get it back. So it's pretty inefficient. There's lots of caching that's done by servers along the way to speed it up, but it's inefficient. And it gets really bad if you're going to do something where, like, every time the person types a character and moves the mouse, there's some information that goes back and forth, which you'd like to have for really dynamic, interactive content. So things like Flash and, well, for example, Flash tries to deal with this problem in some cases by making its own sort of connection that's persistent. But I don't want to mess with that.
This isn't standard?
WebSockets are standard. They would have been much, they were introduced, I don't know, a couple of years ago. People tried to implement them and start deploying them in web browsers, and then other people found major security holes in them and then disabled them. And then the web browser vendors started disabling them and then trying to fix the security issues and re-enable them. So basically, this idea of having a persistent connection between the web browser and a server is something people wanted, and they figured out what they thought would be a good way to do it. But then other people figured out ways of attacking this approach, and I don't know what the actual attacks were, but basically, every time people introduce something involving web browsers, somebody else finds some, or maybe lots and lots of ways are found to exploit it, and these web exploits end up being very costly and embarrassing for anyone involved. And so WebSockets has not gotten integrated into browsers as quickly as you might have expected because of security implications. So the reason you use sock.js is that if WebSockets are supported by the client's browser, and they are supported by, for example, the iPhone, Android 4.x supports it, so Jelly Bean, pretty much all the browsers on my laptop that are modern support it now, even though 8 months ago that wasn't the case. But if you just get like the latest version of Chrome, Firefox, not Opera, not Internet Explorer, but at least Chrome, Firefox, and Safari all support it. So WebSockets are supported by a bunch of browsers now. But there are a few that don't support it. And what sock.js does is if the browser doesn't support WebSockets, it'll fall back to something that is not quite as efficient, but there's a number of different hacks that use iframes or long polling or whatever, which accomplish something that's pretty similar, though less efficient, but far more efficient than having separate connections every time. The Sage Notebook uses this Ajax thing, which is separate connections every time. It's very inefficient. Whenever you type, say, 2 + 2 into the Sage Notebook, the JavaScript client running in your browser sits there and makes a complete HTTP request back to the server and says, do you have any more output? Do you have any more output? Do you have any more output? And it exponentially backs off. So at first it's like every few milliseconds, and it gets, well, every maybe 100 milliseconds, and then it starts getting slower and slower in making the requests. And if suddenly there's some output, then it starts requesting quickly again. But if you have 1,000 people doing that at once, which you actually occasionally, 1,000 people will try to use the Sage Notebook at once, then that's well over 1,000 connections coming into one little notebook server process. and you can't handle 1,000 connections using what we have set up in 1 second. So every single person, no matter what's been, even though they're getting no output at all, they're going to be waiting at least 1 second to get the result of this. And they're going to be sending, their browser's going to send, it doesn't know that the whole notebook server's got slow. So if it's sending a request, hey, is there anything for me, every 1/10 of a second, and the notebook server has received 1,000 of those, and then it'll suddenly become 10,000, and then eventually the clients will start backing off. But basically what happens is it just gets completely saturated, doing nothing. It's a disaster, because you can't handle that many requests per second. On the other hand, if you just have a persistent connection opened, then the web server, when there actually is some output, then it sends a message to the client saying, here's the output. And there's no wasted bandwidth at all. And every time, with the current notebook model, every time you do this request, do you have any more output for me? It's sending like thousands of characters in a header. It sends all these HTTP headers with cookies in them and all kinds of other stuff. Because it's a full HTTP connection, it has to authenticate itself, so it has all the relevant cookies in it. It's just ridiculous. It's much better to just send a few characters when needed. So that's what is used there. This is WebSockets are also used, for example, by the new IPython notebook, but they don't have a fallback. It's like if you don't have WebSocket support, then you can't use it at all.
So these stay open for the whole time you're...
Yep. Yeah, there's exactly one WebSocket connection between the client and the Tornado web server that they're connected to.
And then the whole time I'm on the site, logged into the site, that connection's open.
Yeah, with that particular browser. If you open another, I think, tab in your browser or a completely separate browser, then you can make a separate connection at the same time. But each tab gets exactly one connection. That's one of the limits of SockJS. WebSocket will allow you to have multiple connections to the same server. SockJS just allows one. And so I'm architecting the system so that all information just flows over that one connection, which is a little bit harder, but it makes it more flexible as far as allowing things like Internet Explorer and Opera to work, which is important. I'm also going to have a TCP and SSL way to connect to Salvus so that you can write a program that just uses TCP, completely avoiding using any web browser style technology, directly connect to Tornado, that web server, and otherwise it'll exchange messages just like it would with the web browser. So this will be for writing applications where you want to use Sage or whatever in the back. You want to use Sage under the hood, but you don't want to have to sort of use, say, a WebSocket style library. There are Python libraries that work like WebSockets, but that seems kind of silly when TCP is much faster and so on. So I'll do that. I haven't implemented this though, really. But Tornado is good at asynchronously serving TCP connections in addition to WebSocket connections. So it just has like this data structure that has a list of all connections it has opened, and it just runs around, and whenever something happens on one of the connections, it gets notified by the operating system via some event support in the operating system, and then it does something for that particular connection. And it'll just spin around dealing with a certain number of them. I can run a whole bunch of Tornado processes on the same server to maximize the use of all the cores. Yes?
What does the T in TCP stand for?
Isn't it Transmission Control Protocol? Did you know what CMP stood for?
I'm assuming the P stood for protocol, and
Yep.
I'm guessing connection.
Yeah.
Protocol.
Yeah, I think it's control. Could be connection. But I think it's control. I remember. Okay, so that's everything about client-server communication. Now a few words about virtualization. So, yeah, I've already mentioned this in the previous version. I rearranged the slides a little bit. But basically there's a private cloud and a public cloud. I'll show you a little demo just to give you an illustration of what these clouds look like. So a cloud's just a collection of virtual machines, and there's some ways in which you interact with them that are different than what you might be used to. But for Salvus right now, I have two files that define the collection of Linux machines that are running, some of which are physical hardware, some of which are virtual machines. And then so this file describes the collection of computers. It's basically like an Etsy host file. These are like host names, and they map to a given IP address. And I allow Just like an Etsy host file, I allow the same host name to appear in multiple places. This can be convenient if you want to, for example, ping all the KVM machines, or ping all of the KVM hosts. So you could just ping KVM host and it will work. So there are a lot of machines, as you can see here. The IP addresses all live in, there's 2 reserved IP address ranges. There's this 192.168 that you might have seen before. And then there's also 10.anything you want. That's a huge class A network. And I just use the entire thing. That's also reserved for private use. So basically, I just have this huge network of machines. So then the services file, this describes all the services broken up into different categories. So VM, these are all the virtual machines that get run. The first column gives the host on which the virtual machine is running, and the rest of the line, except for any comments, describe parameters for that virtual machine. So for example, at the UW Tower, which last week when I talked, there weren't any computers over there, but now there are 4 computers over there. And on those 4 computers, I'm running these 4 virtual machines. They have 4 CPUs in each one, 8 gigabytes of RAM, and they're based off of this image, Salvus 1. So they're, the way that, typically with cloud computing, the way that you spin up a virtual machine is you give some base Linux or whatever image that you're going to run. It runs a virtual machine kind of booting off that image. You can change the disk however you want, but when the machine terminates, all of your changes just disappear, and the original image file isn't affected at all. So as you say upgrade, maybe I can make a new image called Salvus 2 that has some upgrades to the system, and then I could restart the virtual machine with this change to Salvus 2, and then it would be running the new one. And I might notice, oh, this is completely broken, it isn't working right, so I could just change it back to Salvus 1, restart the virtual machine, and everything's back to how it was. If you want any kind of persistence, there's another option called disk, in which you could specify a bunch of disk images and their size in gigabytes, and those will be persistent between rebooting of the virtual machine. Just for fun, let's take, for example, 05 Salvus, which, let's see, 05 Salvus, see what the, actually, sorry, the host name is test1. So if you look at test1, its IP address is right here. So I can just SSH to that machine. And now I'm logged into the machine. You can see that's been running for 29 minutes. If you look at top, you see it has 4 CPUs and 8 gigabytes of memory. But I could go back over to this file, and I can change any of these parameters and then restart the virtual machine. So let's make it have, I don't know, 12 CPUs, 24 gigabytes of memory instead. And now we just go back over here. I can do restart the virtual machine with hostname test1. I hit return. What this will do is it kills the machine that was running before, and it's safe to just kill it because, again, the file system on that other virtual machine is completely ephemeral. Doesn't matter. It's when this machine comes back up, it comes up with the root file system in a default state. So you can just kill it. You don't run things on it that need to save their state. The only thing in all of Salvus that ever needs to save its state is the database. Nothing else. Everything else you can just kill it and restart it. It makes no difference. So now I can say status and see if the machine came back up. And this just gives information basically from similar to the output of top for that process. And in particular, it's been running for 39 seconds. So that should be long enough that I can SSH back into it. This thing is dead, but now I can connect back to that virtual machine. Now its uptime is 0 minutes. And if we do top, you'll notice that it now has, wait. What did I do? Maybe I didn't, oh, sorry. It's exactly, the parameters are exactly the same. The reason is because I saved this file, but I didn't reload it into the controlling Python process. So I have to re-import a mod, or I have to reload this. So I have to import that, and then I do restart. So it had just restarted the virtual machine using the same parameters that were there from before. So now it's restarted the virtual machine again using the new parameters, I hope. Yes, you can see in order to run the new virtual machine, it runs this script called vm.py, which sets the virtual machine to have that IP address, store its pin ID file here, its log file goes there, the number of virtual CPUs is 12, the amount of RAM is 24 gigabytes, it's not using a VNC server, etc. And it's based on Salvus 1. And it has that host name. So now again we can SSH to it. If it's come up yet, its uptime is 0 minutes, and then typing top. Now you see it has 24 gigabytes of RAM and 12 cores. So you can just dynamically change things like this, which is nice.
Sorry, I'm still a little bit
Yep,
sketchy.
sure.
The 24 gigabytes of RAM,
Yep.
where do they physically sit?
The computer that's hosting this virtual machine in the UW tower has 64 gigabytes of RAM.
Oh, it doesn't? Okay. Sorry.
Yeah. So if we logged into the computer that's hosting this virtual machine, which is called, I think it's called 04 Salvus. Then type top, you'll see that one of the virtual machines running on that computer is using 20 gigabytes of virtual memory and 1.8 gigabytes of actual RAM at present. Although, I think I might have, actually this is not the one in the tower though. I think that the machine that we just started, there's only one virtual machine running on that computer. So, here it is. So, there's exactly one. It's 29 gigabytes. I guess there's some overhead for that 24 gigabytes. But only 1 gigabyte is actually resident, and 29 is virtual. So.
Can you give access to more? Can you give overlapping access to RAM to virtual machines?
You can. Yes.
So you could, in theory, have 4 things that have
Yep.
access to all 64.
Yeah, except it'll start swapping like crazy if they really start using all the memory. So the machine here, the host is configured with 64 gigs of RAM and a little bit more than 64 gigabytes of swap. And if I use up all available RAM in machines that are actually using that memory, then it'll start swapping them out. And they won't know that they're being swapped out, but they'll be swapped out. So, I mean, they just run like Linux processes. And just for fun, so here we have one virtual machine, test 1. But if you wanted to add a whole new virtual machine, let's just add a bunch. Like, so just this easily we can add 4 new virtual machines and give them some names like this. And then over here we have to specify their parameters. So they run on 05 Salvus, but they have host names 1A, 1B, 1C, 1D. Let's give them all 24 gigabytes of RAM and 12 cores. So that's a bad idea because there'll be contention, but we can do that. And now I just reload this, and I do s.start. I want to start all the VMs that run on 05 Salvus. Status, sorry. Actually, let's do that first. That'll give us the status of everything running there. It should be one's running and the others are just not running. So that's why it gives an empty output. That means they're not running except for the one that is running. And now let's actually run them. If I do parallel equals true, wait equals false, it'll in parallel start them all running, and it doesn't wait for any sort of output to come back. This doesn't matter much when you're starting at 4 machines, but being able to do that matters if you're going to start like 100 machines at once on 8 different computers. You want to just start them all running simultaneously. Okay, now I can do status again, and you can see that they're now all started. If you look at top, there should be, let's see. So now there's several different KVMs running at once for all these different machines. We should be able to SSH into them. So let's see, what were the IP addresses? .2, .3, .4, .5, and .6. So we can do .3. And there it is. This is another machine. And it has the same parameters. And you can notice that the host name is test1A. So if you want to start up a whole bunch of new machines, it's that easy. I intend to use this, so I developed this, these 2 files, like the scripts to manage the VMs using these sorts of files after looking at a bunch of private cloud management systems. That's what I'm talking about here. I guess in the next slide. There's these things called OpenStack, CloudStack, OpenNebula, Ganeti, and so on. And like if you look at their websites, it's apparently a huge business right now. So let's look at OpenStack, for example. So they have all these fancy websites. This whole idea of buying a bunch of computers and then turning them into a private cloud is very exciting to people that want to sell stuff or give it away. If you go to even the Ubuntu website, it's pretty weird what you'll see there.
I have a good friend down in the Bay Area who works for a cloud company called Nebula.
Nebula, that's probably one of the ones I listed. Open Nebula right there.
N-I-M-B-U-L.
Oh, what is it?
Nimbula.
Nimbula.
I'm guessing
Do they, so, whoops.
Nimbula.
Nimbula. So here's Open Nebula, which is another one. Not yours, but I guess, I don't know. You can tell that there's a lot of industry excitement, all these things. But the really weird thing is I installed all of them and didn't think they were very good. At least they didn't seem to solve my problems. Like they had really clunky web interfaces that you were supposed to use to get work done. That kind of look like, so Amazon has their own thing that's kind of like this, where you go to Amazon Web Services, AWS is the name of the website, and you can create a virtual machine, you can turn it on and off. There's a Python and other language APIs that let you automatically start lots of virtual machines and stop them. So Amazon provides this. And the idea here is that people might want to do the same thing that they would do at Amazon, but on their own computers for either cost reasons or data security reasons. When you stick data on Amazon, that might violate your company's policies about how data is stored. So there are people building all these bits of software, but it's not very ready in my experience. So like Ubuntu, pretty weird. They have they're really behind this OpenStack one, but let's see, where is it? They have a link to build your own private cloud, and they want to charge you a lot of money. It's like thousands of dollars per machine, or I don't know. It just seems really expensive. Building your cloud is easy. Just get our on-site canonical engineers and give them like $10,000, and it'll easily get done. It's stuff like that. And I don't know. I can see how it could be a big deal right now. It's a good idea because basically, if you don't approach building your website using this kind of cloud infrastructure, then what you end up getting is so I'll leave it at the Ubuntu one. You don't build your website doing this, then you end up just buying a whole bunch of different computers to do different things. And I in fact was thinking about doing that when I was setting up Salvus. So you think, oh, I need something to do SSL termination, but for security reasons, I need the machine that does this has to have its own firewall. The machine that does the database, since you don't want anyone in the outside world to connect to the database, so the machine running the database has to be a separate machine, separate computer with its own firewall. So you need like 4 machines to run your database. So you start realizing you have to buy 20 different machines. It's sort of forced on you by redundancy and security issues. But when you set things up using lots of virtual machines, you can basically accomplish your same security and redundancy goals, but without having to buy a large number of physical machines that are going to be massively underutilized.
So how does that,
it's popular.
like,
It's really popular these days.
I understand, I mean,
yeah.
That all makes sense to me except for the virtual machine, the security, or the redundancy thing, because like, if you have a bunch of virtual machines.
You don't run them all on the same host. So you still have to spread them out a little bit, but let's say you want to have...
Like a hardware failure.
Yeah, it brings down a bunch of virtual machines, but let's say you need to have 2 S-tunnel servers running to take incoming traffic from the outside world. So you could buy 2 physical computers, or you could run 2 virtual machines on 2 separate computers. The actual hardware is separate. So if you had 5 different components where each one requires 2 machines for redundancy, then you have 10 physical computers. You can map those 10 physical computers to 2 physical computers and 10 virtual machines. And then when one physical computer goes boom, half of your infrastructure just died, but at least the other half is still up. And you wouldn't want to do it with just 2. You want to have more like more than that. So you can satisfy the same redundancy requirements with that, but by making more efficient use of the resources. In any case, it's not like some new idea at all. It's just very popular during the last couple of years, and you'll see it all the time if you look in the news for tech stuff. And a lot of people don't understand it and make fun of it, but it's actually a pretty good approach, this cloud computing idea. I mean, it's just, you can see very naturally how it evolved. And it's also very affordable now because, I think, in my opinion, mainly because Red Hat put a huge amount of effort into developing completely free and open source software that's now included in the Linux kernel for managing virtual machines and creating them and so on. Before that, it was mainly VMware, which charged a lot of money for the same thing. Okay, so yeah. So anyways, you can see how easy it is to add machines. So like you start realizing a lot of people are running Sage, and you just want to add a whole bunch more machines to do something. And this is what we do. You can also do things like regularly snapshot a machine. One plan for a service I want to provide is Salvus. It's not mentioned in the slides for the talk, but I've been talking with various mathematicians lately, and it seems like this would be a killer feature. Is imagine you could start a calculation running and then be very certain that 8 months later, that machine that you started the calculation with, that process is still running. There's certain applications, like trying to find points on an elliptic curve or whatever, where that would be a really nice feature to have. And the way I could provide that with Salvus is the calculation would start running on a little virtual machine, and that virtual machine would be snapshotted maybe once a day, or you would adjust a parameter. While it's being snapshotted, which might take 20 seconds, the machine has to pause. So you have the frequency of snapshotting will slow down your calculation a little bit. So you have to choose what it is. What it would do is it snapshot the memory state of the machine and save that in a database regularly. And when the machine crashes, or rather the host crashes, or when something goes horribly wrong and I have to power down the host to upgrade the operating system or whatever, all I do is when I restart that virtual machine, I start it at the state that it was at before. And since the state will be stored in a database that gets replicated, you can easily just keep one single machine running indefinitely. So some people, they don't want to try to understand how to save partial output from MW rank to disk and make it restartable or whatever. That would be very difficult. But with a service like this, they could just say, hey, I'd like to run this calculation for the next year. I pay for the resources to do that, and boom, it starts, and then whenever it finishes or whatever outputs they get it. Could you see how that might be useful? Have you ever run anything? See? It's really, really clever people can break up their calculations, write a low code from scratch so that everything is checkpointed and so on. But some people are just users of software. In fact, most people. And this is what they really want.
Ask Sarah Billy about that.
Yeah, this came up with when I was talking to Combinatorics people about what they want to do with the new Sage Combinat machine. So it's exactly that sort of thing.
She said she proved a theorem where basically they enumerated that they found the only 300 of these things that exist by writing some program and then letting it run for a year.
Yeah.
And she was like, how do I, in good conscience, get this refereed?
Yeah.
Because the referee would have to write an independent program and
then
let it run for a year.
And what computers have a year uptime? Right. That's very rare. It's considered bad form to run a publicly accessible server and not reboot it regularly, because a lot of security updates, like if there's some weird security issue with the Linux kernel, you have to reboot your machine. Except there was a company that, just a quick aside, there was a company that made it so you could update the Linux kernel without requiring a reboot. That was their entire startup company. And it was written, Tim Abbott, who got Sage into Debian, was the same guy that started that company, strangely enough. And I think that company got big, and he stopped working on Sage. So I never really liked that company, but because he worked on Sage a lot before the company. In any case, normally you have to reboot your servers for various reasons. But this virtual machine, I wouldn't need to make it secure because it's sitting on a private network. It's firewalled. It's not, even if there is some discovered vulnerability that requires a reboot to fix, I don't need to do that because it's just, that's fine. It doesn't matter because it's not exposed to the outside world. So that's one of the features I'd like to add. In any case, one thing is I want to stop all these machines I started before I delete the definition of them. Because if I delete their definition, currently this doesn't have any sort of database that sort of saves everything that happened. And so if I delete the definitions of things that are just kind of lost running, there's no database hiding behind this particular administrative interface.
You would have to go over and restart.
No, I'd have to just log into the machine. I'd do something like kill them manually. Okay, Okay, so that's it for cloud stuff. Okay, maybe I'll show you really quickly this vm.py script. So, oh, that's dead now. Or at least, here's the output. So this is a script that I wrote, it's a few hundred lines, and it coordinates making virtual machines, setting them up so that they have a certain IP address on the virtual private network, and so on. That actually probably took the most time, setting up all the VPN stuff to be completely automatic and robust. There. Okay, so that's just the output of that script. Oh, speaking of VPNs, so I think I talked about this enough before, but yeah, maybe I won't say anything more, just that I'm using Tink for the VPN. And I'll just show you the Tink website momentarily. So this is the Tink website. So you've probably never heard of it, but it's been around since the 90s. And it's really, really cool because you just, all of your machines that are publicly accessible on the internet, you make them Tink servers. And all other machines connect to all those Tink servers. And then if all but one of the Tink servers dies, you still have everybody connecting to everybody. So I have like 10 different Tink servers that are publicly accessible on the network, and my network can survive the failure of 9 of them. So it's really, really cool.
So which machines do you make to publicly available servers?
Just all my virtual machine hosts. So I have 4 hosts over in the UW tower. They all have public IP addresses, and so they're all Tink servers that are publicly accessible. The 4 hosts downstairs are combinat.mathwashington.edu geom.math.washington.edu. And basically they're running a server listening on port 655 for a Tink connection. They accept connections exactly from computers that, so basically they have a list of, I'll just show it to you. It's easier to show it to you than to describe it. There's a list of files that are public keys. So I'll look at the one on, I don't know, 01 Salvus. This is one of the servers. Again, yeah. So make that bigger. Move it up. Okay, cd Salvus local. Actually, better yet, conf Tink hosts. So this is a list of, or this is a collection of files, one for each computer that's allowed to connect to this particular Tink server. So all the computers listed here, each file contains a public key. So for example, geom can connect. Geom has this public key, so I'm giving away nothing in showing you a public key. That's a critical public key. So the computer at that address with that IP address, and that can prove that it knows the corresponding private key for this public key, is allowed to connect. So the only reason that that computer downstairs lets this client connect to my network is because I physically put this public key file on that computer. So if you want to add a new client, you have to add this file to each of the servers to let them connect to it. So basically the way it works is I have all of these virtual machine hosts in various places. They allow connections between each other. And when I start up a new virtual machine, it only connects to the host it's sitting on. It doesn't connect to all the other Tink servers, because that would be pointless, since if the host that the virtual machine is sitting on is somehow down, then the virtual machine is down. So there's no point in doing anything further. So you can imagine the topology looks like this. So you have a virtual machine host, 01 Salvus. So this is a physical computer sitting in the rack downstairs, and it has a bunch of little virtual machines running on them, and it's running Tink. And then you have another Tink and virtual machine host over here, and another one. And there's basically a complete graph connecting all the hosts together, but the virtual machines they're just connected like this into the Tink server on this one particular machine. So anytime if this virtual machine wants to send some traffic to a virtual machine running over here, what happens is it sends the traffic through, it sends it to the host, encrypted, and then it gets encrypted and sent to this one, and then it gets sent to this one. So.
But you said this, if 9 of them fail.
Yeah. So what I mean by that is, so the thing is, if 9 of them fail, if there's some machine out here that's connected, so it's one of the other hosts, like from the UW tower, what it does is it connects to all of the other hosts. So if like this one goes down, then this one can still communicate with all the virtual machines and all the other hosts. However, it can't communicate with the virtual machines in this one, which is okay because this guy is down. So, and my laptop, for example, my laptop is connected to this VPN. It's it's defined by one of these files. It's called
Doesn't that give us
Salvus 0.
an n-squared dependence in terms of number of connections between servers?
Yeah,
Yes. And so
but n is not very large.
n is not very large.
That's
so
okay.
we don't care about scaling.
Well, what matters is the number of connections from a given server. So, so there's going to be hundreds of virtual machines, but the number of hosts is on the order of 10 or 15. So having 15 connections is fine. So,
I mean, even if you somehow ended up with 1,000 hosts in the future,
Yeah.
you wouldn't necessarily have to have them.
exactly right. I get to choose. I mean, I could just take a random subset of 10 and decide this guy's going to connect to that random subset of 10. I could choose like the 10 closest or something in some way, or just randomly choose them.
The 10 farthest to deal with geographical things.
Exactly, or 10 uniformly distributed in some way. So yeah, you're right about that. In any case, you have the flexibility of making choices like that with Tink. Whereas an OpenVPN, you would set up one single machine to be the OpenVPN server. You would connect absolutely everything to that machine, and all traffic would flow through that machine. And you have to set up a whole public key infrastructure that involves that machine generating keys that it gives to other people, which gets complicated. I mean, you do have a public key infrastructure here, but with Tink, but I think it's really natural and easy to understand. Their documentation doesn't make it seem easy to understand, but once you understand it, it's really easy to understand. Yeah. The documentation, it's kind of weird. I think it's all written by Dutch people, and I think the authors were Dutch. And I don't know, it's just something, it's not very good English, even though everything's in English, but it's not the best English. Usually Dutch people are really good at English, whatever. In any case, it's very clever, and it does things like, if this one wants to talk to this one, it doesn't take like the longest path. It tries to take the shortest path from one to the other. In this case, there's a direct connection, so it's not going to route all the traffic from here to there through the middle one. It will actually use the direct connection that we set up. So. Okay, so moving on. Oh, speaking of speed and so on, here's just an example. So let's see. This command ping all. This will ping every single virtual machine, and it gives back the ping times. So I think the first time is the ping time. So that is information about how long it took from my laptop to ping all the machines. And some of these machines are in Fidelford, some are in the UW Tower, some are at servedby.net, and you can hardly tell the difference between any of them.
So this ping had to go out over the VPN?
Yes, it entirely went out over the VPN.
Because I couldn't find any of those IP addresses.
That's right, they're in a private network. I can also run this ping from, so running it from my laptop isn't as fast because it's a Wi-Fi connection, and that's actually slowing everything down a lot. If I do it from here, I've now logged into one of the virtual machine hosts downstairs, and this ping should be substantially faster. Yeah, notice all the ping times are like on the order of a third or a quarter of a second, which is a lot better.
So that's in seconds.
Yes, yeah. So, and just for example, served by, so these are a little bit longer. This is at some external public cloud. That's where those are. 05 Salvus and 06 Salvus, these are over at the UW Tower. Let's see. This one's sitting downstairs. That's a virtual machine downstairs. This is something over at the UW Tower, 23. But it's really, there's very little difference between the time at the tower right here. And the transfer time, if you just, I just did some network benchmarking, and you can't tell the difference with like just sending a large file between two machines downstairs in the server room and a machine in the server room downstairs and a machine at the tower across campus. Like they're both, the benchmarks look exactly the same, which is really nice. It's really good at networking. Except for when I set up all the computers the day before yesterday, one of the machines was like 10 times slower than the others. And it turned out that one of the Cat6 Ethernet cables I had bought just was not working right, and so I had to toss that. So I put a different Ethernet cable in, and it was the right speed. So, yeah, it was the green one. So, you really got to watch out. I had no idea that just plugging in an Ethernet cable, every time you plug in an Ethernet cable to connect two machines, if you care about the speed, you actually have to do some tests and look at whether it worked correctly or not. And you can have huge performance issues with the seemingly correct Ethernet cable just because of quality variation in the cables. So I didn't know that until a week ago. Okay, so that finishes VPN stuff. Oh, one other remark actually I wanted to make about the VPN is I've set this one up for Salvus, but I want to set up a similar VPN for Sage development, where instead of all these Salvus machines in this network I've been describing, there would be another network which is a whole bunch of machines all over the place that are meant for Sage development activities. So testing Sage, build bots, stuff like that. Could be machines in people's offices, it could be whatever. And it will be one of these virtual machines with a whole bunch, or sorry, one of these physical hosts with a whole bunch of different Linux OSs installed on it, for example. So that will get used for Sage development. So you just send me your public key. I would add you as a loud client. It gets stuck in several of the servers and install Tink on your laptop or your desktop, whatever computer you have. And then whenever you open your computer, you could just connect all these Sage development machines easily. So I think that would be nice. Yeah. Okay. Okay, moving on. Databases. So in all of Salvus, the only really persistent thing running when the system's actually running in the infrastructure, in the overall stack that I showed you. Besides a couple of files that define the overall layout and the source code of Salvus, which is also persistent. But the only really persistent thing that has a state itself is the database. So I tried very, very hard to use Postgres or really any relational database to design the system. I used it a lot, for example, at when we were in Utah at that conference. I would be very familiar with it, and I got really good at using Postgres, and we did a bunch of research using it. It worked well, but basically, and if you look at books about how to write scalable web applications, they always assume you're going to use MySQL pretty much across the board. And if you look at what big websites actually use, it's actually very often MySQL. For example, Twitter uses an enormous number of MySQL machines or servers running MySQL. So MySQL is extremely big in production. But basically, the way you use these relational databases is you make a whole bunch of different databases and you figure out how to store your data on all these different databases in some clever way. And it seems like a lot of work. It's tricky and confusing, and it seems like a whole art form, which I'm not saying it's a bad idea. For example, Twitter makes very successful use of this approach, and I guess most websites, or a very large number of large websites do, but it seems really hard to me, and kind of, maybe just because I'm a mathematician, it seems kind of ugly to have to basically to have a whole bunch of little databases when you should be able to just have one single conceptual database and have all the technology for spreading it amongst various computers be done automatically. So in any case, I tried very hard to come up with a system using PostgreSQL, and I ended up designing something where we'd have a whole bunch of different PostgreSQL servers running, and when you save data, they would send the saved data out to a couple of other servers for redundancy, and I sort of came up with this whole clever design. And it was partly because for the nth time, the Delford server rooms basically blew up, and all the power was gone for a day or two. I decided that I did not want to have any single point of failure, so I don't have one database running somewhere where all the data is stored there. Okay, so So it's a situation I don't want to have any single point of failure. The standard way with PostgreSQL, for example, or MySQL, that you can eliminate a single point of failure, henceforth I'll refer to as an SPOF, is you have your master database, and then you have a slave, which is a second database that looks just like the master. And anytime you do a write to the master master database then sends a message to the slave saying, hey, do the same write. So it's a pretty straightforward idea, but you do lots of tricks to make it faster. These databases have pretty good built-in support for doing this sort of automatic slave-master stuff. And then what they do is you think, okay, great, I have a sort of automatic backup of everything that's stored in the master, but what happens when the master fails? It's never if the master fails, it's going to fail. So the question is, what happens when it fails? And there's two things you can do. Either you have automatic failover, so you have some program sitting there that will decide, hey, the master database failed, and so I'm now going to switch to the slave database. I'm going to tell every program that was accessing the master that now you have to access the slave, and I have to somehow switch over to using the slave until the master gets fixed and then it switches back. And you have to deal with that sort of thing. It's very hard to decide when a piece of software has failed, as it turns out. You think, oh, that should be really easy. But in fact, computer scientists, they do research in computing. Apparently they do a few useful things, but they do things like, how do you come up with a good algorithm if you have a whole bunch of programs running? How do you decide when one isn't working? It could just be that the network is temporarily slow. Or it could be that the one particular program is working fine, but it's heavily loaded. Or it could be it really just died, and you don't know which of these situations you're in. And there are papers that are about methods for, instead of deciding whether a program is alive or dead, based on some like hard and fast rule, you come up with a kind of conditional probability, a conditional health for your program over time. So you have some formula that you're constantly iterating that gives you a sense of the probability that the machine is working okay. And if it gets really bad, then you might take measures. In any case, just deciding whether or not something is healthy is a subtle problem in and of itself, and there are sophisticated algorithms for trying to decide this that are more sophisticated than you would think, possibly. And then here's an example. Very, very recently, GitHub went down for a while, and it was caused by their automatic database failover. So you can read a message about this, or an article about this. Somebody says, I'd like to welcome the GitHub operations and database administrators to the club of people who have learned the hard way that automatic database failover usually causes more downtime than it prevents. I think their master database failed, so then it automatically switched to a slave database, and it ended up that for some reason that ended up causing lots more problems. So people had to get involved, and it ended up being a big disaster. So this happens a lot, and these companies often have an operations team, so they have a bunch of people that are supposed to be watching this sort of thing. So Twitter has a lot of people presumably who deal with database failures and so on. So some companies, they don't do automatic failure. If there's something going wrong, a person's notified, they look at it and decide, should I fail over or not? That's their algorithm. And if you're a big enough company, that's completely reasonable. For me, on the other hand, I definitely don't want to do that. So finally, after getting really annoyed by the whole database difficulty, I had completely so I learned about NoSQL databases. These are databases that don't use the SQL query language, don't use the SQL approach. SQL, I don't know how much you know about it, but basically you have a whole bunch of tables, and you have relationships between the rows of the tables. It's very relationship-based, where in order to do a query, you often will consult 5 different tables in one single query. Like you'll look up, you want to find the last time a user logged in. So what you do is you look in one table for the ID number of the user, then you look in another table which has ID number and last login. So you're looking at 2 separate tables, combining the information together to get the information of when the user with a given name last logged in. The NoSQL databases are, one of the key things they do differently is they make it very, very hard to do this sort of relational lookup. Instead, what you do is you have a table which would have the username and the time they last logged in, and the username and something else. Or you'd have to do 2 separate operations, look up the user ID, and then a separate lookup to get the last login from the ID. They seem less powerful, and they make it harder to do certain things, but they force you to make your data a little bit more redundant so that when you're doing a query, usually you have all the information in one place in the database. So I don't know, I thought that was sort of a weird curiosity, and I learned some about it, and it seemed kind of natural for storing, I don't know, like mathematical objects at least. But I really didn't understand at all why these things were getting popular at all until very recently. And then I realized, or when I was looking at this again, it turns out that one of the main motivations for NoSQL databases is that you come up with a database model where the functionality is far less than what you have with SQLite or Postgres. However, you have a plus. In giving up a lot of the functionality that you have with the other systems, you can make it pretty easy to implement something where it runs on a whole bunch of computers at once, where anytime you store data, it gets stored on n other machines automatically, so that if n-1 and you get to choose the n other machines disappear, then your database continues running fine. So you have this sort of functionality with some of these NoSQL databases at least. There's other things about them, but that's the main motivation that got me back into them. I learned a lot about MongoDB. I got the LMFDB project to use it, and then I kind of got sick of it when I started using a lot for my own data. I tried to back it up. It doesn't spread itself out over various machines very well. It has kind of in a way it has all the bad aspects of NoSQL and none of the good ones. So it's just very easy to get going with, and it has a lot of salesmanship behind it. There was a post a few days on Hacker News, which was, let's see, I guess I can't change the font size. It was just called "Does NoSQL Suck?" Or sorry, does everybody think MongoDB sucks? That's this post right here. Does everyone hate MongoDB? Because there's just a lot of people complaining about it these days. In any case, there's another database, kind of like MongoDB, another NoSQL database that's called Apache Cassandra. It's open source, it's released under the Apache license. It's used extremely heavily by Netflix now and by Disney and many other companies. What?
Reddit's a big online.
Reddit? Yeah. It has a large number of famous users. It was written by Facebook, and it's really cool. I mean, basically you can run it on a whole bunch of different computers, and you save stuff. I'll just show you me running it. So I have it running here, and I'll connect to, I was hoping it would be in history. Yeah, it is. So I'll connect to one of the Cassandra servers. There it is. I can do a query. It looks like SQL, as you can see. So this query selects what Sage servers are running and where are they running. What are the IP addresses of the running Sage servers? Let's see. I forget what the name of the other. There's another table. Let me look it up in the database. Stateless exec. Okay, there it is. So I just do another query from the database. Stateless exec. So this stores, for example, when people evaluate code in the Salvus website right now, where people's almost certainly always me, this stores the calculation that they did and the result. So you can see how these are being stored in the database. This is a Cassandra cluster that's running on 4 separate virtual machines, and but I can expand it to more machines if I want. It's easy to monitor the nodes, so this shows, what this does is it, whoops, what did I do wrong? Weight equals true. So this shows 4 different nodes, something about their location, how much data is stored in each node, and there's a token. It takes a piece of data that should be stored, which is basically like a row in a table. It then computes a number, a hash of that data, and then based on that hash, it stores it on n of the nodes, where I set n to be 3 in this case. So all but one of these 4 nodes will get the data. And when you do a read, you connect to one of the nodes and say, I'd like to read a row from a table or do some sort of query. And it will say, it'll either check to see if it has the data itself, or if it doesn't have the data, it'll get it from the appropriate one behind the scenes, or from one of the appropriate ones. It's actually, there's a really subtle problem that, I don't know if it's popped into your head yet, but what if a client connects to this one and writes something, and then this one, and a client connected to this one reads that same thing a millisecond later. What answer should you get? So there's a consistency question in that, you write, hey, this person just made a bank transaction, their account has this much in it, and then the other node reads, and they haven't quite synchronized yet. So this sort of synchronization business is extremely subtle, and it turns out that there's a theorem called the CAP theorem, which says that you can't do everything you want regarding simultaneously writing and reading and so on, but you can come pretty close as long as you acknowledge the difficulty of the problem. You also have to decide what you're going to do if the network breaks down in a way that you end up with a split brain, as the computer people call it, where you have half the nodes on one subnetwork and the other half in another network, and there's no connections between them. And then you start having writes separately to each side that are conflicting. What do you do when it comes back together? So you have to come up with algorithms to decide that. So there's actually a lot of really interesting and subtle questions in distributed databases, which I plan to not worry about. Just enough that I understand how it works.
Since you're not a bank.
Exactly. Well, I mean, security of data does matter somewhat with Salvus, but it's not too difficult compared to what banks have to worry about. Although banks actually do this sort of distributed database stuff with ATMs, where ATMs are extremely distributed, and they want to make it so you can do your transaction without having to potentially wait a long time. So they're not like worried about constantly synchronizing everything and always going back to a master database. So they'll allow some transactions potentially that could make your balance negative, apparently. According to an article I was reading about distributed databases, bank ATMs
for example,
they'll like tell you, oh, by the way, you actually owe us money now because we let you make this transaction you shouldn't have done. Yeah.
I mean, if you duplicate your card
Yeah.
and send a friend across town to draw money at exactly the same time as you,
Yeah.
off different ATM.
Right. It could potentially, you could end up with a negative balance.
Yeah.
And it's just worth it overall. They'll make more money by letting you do your withdrawals very quickly than making sure everything's absolutely consistent all the time. So ironically, one of the big examples of not requiring your data to be consistent immediately is banks.
There was
Just
a
eventually consistent.
very interesting article about this, I think 2 years ago, so where a European crime syndicate exploited this very fact.
Wow.
Got a whole bunch of credit cards, duplicated them like crazy, and sent out criminals into various parts of like all over Europe to do simultaneous
Wow.
cash withdrawals. And
Wow.
because there wasn't instantaneous synchronization, ATMs managed to steal millions and millions of dollars.
So,
I think there were a bunch of Russians.
yeah. Dang, that's really cool.
You gotta go take care of something.
All right, S-tunnel, just about how the SSL stuff works. I mean, there's a program that sits there and receives SSL connections, and I don't know. Basically, making your site use SSL securely works pretty easily if you're careful, and that's why when you go to, when you go to the Salvus website, it says HTTPS, and it has a nice green lock icon. It's not all. There's no terrifying message saying, "Oh my God." Whereas if you go to one of the underlying servers that has, so this is really running on 01salvus.math.washington.edu, that the security certificate that it just gave my laptop was signed for salv.us. It wasn't signed for 01salvus.math.washington.edu, and that's why I did this message. And this message is terrifying, and people won't want to use the service if it has that message, even though it would work in the same way. Okay, so moving back, say no more about SSL, except that it's really not that hard. HA proxy is what I'm using for load balancing, and so what happens is computers connect to S-tunnel. S-tunnel just immediately proxies everything over unencrypted to HA proxy, and then HA proxy then decides on which of the many potential Nginx servers and which of the many potential Tornado servers are going to get these connections. And it depends on what sort of request it is to which HA proxy or Nginx server gets used. Actually, I'll show you the HA proxy config file, since that's helpful to understand what's going on. Conf HA proxy. This is the template that it uses. So there are lots of parameters about how long until a connection times out, etc. There's some coding here that decides whether or not the web browser is a mobile browser or a desktop browser. If it's a mobile browser, it returns static content from one directory. If it's a desktop browser, it returns static content from a different directory. So I have separate HTML for mobile and non-mobile. And then when the content is static, then it uses Nginx, and this little thing it's a template that gets filled in with the actual Nginx servers that are defined in that file. And then when the content isn't static, it uses a tornado server, and again, there could be lots of different tornado servers, and it'll just use one. I can adjust which algorithm is getting used using this load balance thing. And I think right now, apparently it's who it connects to is based on the IP address they're connecting from. But you can also adjust it to be round robin or something else. So it's nice because this one program, HA proxy, that's where you put all the logic about how the load balancing works, instead of putting it all over the place. Etc. And the insecure redirect, if they connect to an insecure port, then it redirects them to a certain, maybe to the secure version of the site. Okay, so that's HA proxy. There's Nginx, which is competing now with Apache for being the biggest, most popular web server out there. It's super, super fast, and it uses an absolutely massively different approach to the problem than Apache uses. With Apache, somebody connects to you, Apache will fork a subprocess that will then respond to the request, and then the subprocess terminates, which is fine to some extent, but it ends up being fairly inefficient if you're going to try to respond to 1,000 requests in 1 second. And with Nginx, instead, they just have one single thread that just sits there and does a little bit of the response kind of in a circle to each of the requests. It just responds a little to one person, then moves on to the next, and just keeps one single thread, just all the logic for switching between handling a request from one person versus another is done in the Nginx program itself, rather than by the operating system switching between different processes or threads. So there's a big thing on the Nginx website explaining why that results in far more efficient code. So I'm sure that Apache's probably changed to some extent to take advantage of this sort of idea. I don't know. But what Nginx does is it has this one single thread, but then you think, oh, I have a computer with 16 processors. How can I take advantage of all 16? So you just run 16 Nginxes at the same time. And if you have a load balancer like HA proxy, it'll decide to send a request to one of those 16 in some sort of sensible manner. So it'll spread them out. So anyways, that's how the static stuff is handled. And if at some point I wanted to move the static handling off to what's called a CDN, a content delivery network, these are also really popular, where various companies have servers all around the world, and they'll let you take a chunk of static content and just stick it all around the world on their servers. And then whenever a user requests any of that static content, it will find the closest server in the world to them, and then look at the static content from there.
So
and
what's
pay
an
them for
example
this.
of static content?
Okay, I'll show you an example. When you go to the Salvus website, the warning message, the word Salvus right there, that button, the JavaScript that is being executed, this is all static. The dynamic content is, when I type 2 plus 3, that 5 that appeared right there. That's dynamic. So, and then physically, what this is, I mean, it's just the stuff that's stored in this directory static. It's a bunch of JavaScript and HTML. So for example, this file index.html, which says, this is an extremely preliminary demo, and it gives you a little box that you type into. This is static content in that
So like my
everybody sees the same thing.
website is static.
Yeah.
Because they're just,
It's always the same.
Yep.
It doesn't need to do a calculation to decide. There's no like sophisticated work that goes on to figure out what HTML to send out here.
So it's the same HTML every time.
Yep, exactly the same HTML. The one subtlety is when you do language, like when you do internationalization, you might do it dynamically, and that's popular with a lot of web servers where they'll write little templates, so it'll figure out what language the user is using, and then it will dynamically generate this page, for example, but in each language by filling in templates. And that's actually really heavy on the part of the web server, because it has to sit there and every single time an HTML file is accessed, it has to compute the version of it for that language. And this is how the Sage notebook is right now, actually. All the HTML is templated like that. I'm not using any templated HTML at all. I just have the static directory that's truly static. I could stick it anywhere and it would work. When I want to do language support, I think I'll serve up the language customizations separately, dynamically, and let the web browser of the user fill in the different languages. So they'll get a static page, and then some JavaScript will run, grab something that describes what the customization should be for their language, and then it'll do everything. So it'll offload the work to the browser rather than my servers having to do it. So I'm not a big fan of this approach where you write lots of templated HTML that is specialized for each different user by the server. I'd rather the user's browser do that work. Because that way I could just, all of this HTML, there's going to be a lot of it. It gets really big after a while. You write a lot of JavaScript and HTML. And I'll just be able to stick it on a content delivery network, and then when people try to visit the site, they'll get that content. The initial page load will just be super fast, because it's going to load it from the closest cache. So that's what I'm thinking. And then maybe the language translation part, that'll take a little bit of extra work to get. Should be pretty easy. Does that make sense? Yeah. Okay. So that's Nginx, which, again, I want to be able to swap out. Here's Tornado. This does dynamic content, which is like the 5 that appeared. So it's the dynamic stuff that comes out later. Tornado, you can find their website, tornadoweb.org. It's a pretty stable project, all written in Python. It basically, I mean, the best way to think of it is there's this web server called Twisted. Right? Well, it's actually a lot more than just a web server. It's this ridiculously complicated Python library for doing everything that involves asynchronous network-based programming. And it happens to have facilities to be used as a web server. It was what the Sage notebook was written using until very recently. Tornado is kind of similar in that, but it's just asynchronous web server and nothing else. And it's completely written from scratch, separately from Tornado. So that's what it is. The main reason I'm using it is because it's really, as far as I can tell, the only reasonably mature Python web framework which supports WebSockets, which I want to use. In fact, that's the main use of Tornado for me is the WebSockets type stuff. So, so it sort of sits in the middle there. It was written also by Facebook and open sourced. So there you are. Oops. So IPython, they have a notebook, which is kind of like the Sage notebook. It uses Tornado for its web server. Tornado is fast. It's very event-driven. So instead of having little loops that are like, "Are you ready to do something? Is there anything for me to do?" You know, that sort of like polling base, which everywhere in the Sage notebook you'll find polling happening all over the place. Tornado is very event-driven. You just sit there and wait and find out when an event occurs, then you get notified and a function gets called. That's how Tornado works. So I've tried to make that kind of an axiom in the design of Salvus all over the place, that everything should be event-driven rather than polling. Polling works, but it doesn't scale up. And event-driven programming is only an option because, I guess, in the late 90s, people thought really hard about how to make operating systems support event-driven programs. So they want to make it so that when a file changes, your program gets instantly notified. So imagine if you wanted to write a program that would sit there and watch to see when your tech file changes and automatically tech it, which of course that's the way it should work, right? Every time you save your file, it should just automatically get teched. But like I've written scripts like that, and what I do is I just keep looking at the file system, checking to see the modification time of the file, and when it changes, then I tech the file. But there's a better approach, which is you can hook into a certain library, a certain function. You can say when that file changes, have the operating system just call this function, regardless of what's going on. And turns out that's been made very, very efficient in Linux, for example, and in OS 10. Okay, so we're almost done with all the things. So here's Sage. I wrote a TCP server version of Sage, so I'll show you that really quickly. So Sage server.py -help. was a little too big. So sageserver.py, this is the help. It starts up a Sage process that listens on a TCP port, and you can connect to it and then type commands, and it will give you back the output as the output appears in a sequence of messages. All the messages that it sends or receives uses Google's protobuf format. It's a binary format for sending messages and for describing messages that Google uses a huge amount internally, and they open sourced it. And just to show you how this works, you can say, start a Sage server listening on whatever the address of this computer is. So this is 1038.11, and I'll have it listen on port, I guess it's -P6000. Okay, oops, sorry. You have to run it under Sage. That was just Python, so Sage. Okay, so, what? Let me do that. Oh well, I guess I can't run it on my laptop using the Sage installed on my laptop. But I'll run it on this, this computer right here. So the same command. So same command, except I don't have Sage installed here, do I? Yeah, I do. Okay, there. Oh, I don't have Google, I don't have protobuf installed into this Sage. All right, so in any case, in theory, I could run it, and then that's all you do. You start running like that, and then you can connect to it. I have a bunch of them running as part of Salvus. They're listed here under Sage services. So they're all the hosts that have Sage in their host name right here. So for example, here's one of the Sage servers that's running, 10.1.1.4. So I should be able to do Sage server dash help. So I can do run in client mode. I want you to connect to that host with that port. So what that just did was, on my laptop, I initiated a TCP connection with a virtual machine running downstairs that's running one of the Sage servers in a virtual machine that's set up for running Sage servers. And now I can do a calculation like 2 + 2. I could do ask for the host name, and it's Sage01, which is one of these virtual machines that's running, etc. Or you could do for I in range. Well, it does pre-parsing and stuff. Print I sleep 0.5. And see how it's giving you output as it goes. And also notice the startup time isn't very bad. So that's the time to make a connection to the remote machine downstairs, run 2 + 2, and terminate this and everything. It's still 0.2 seconds. So it's a lot less than just starting up Sage on the laptop. Because what it does is it makes a new Sage process to handle each computation or each session, but it's just forking from a single process. So it's very efficient. So it works really well. Pretty happy with it. I think I'll include it in Sage because it imports the Sage library. If I distribute it, then I have to GPL it because it's because Sage is GPL'd. And I think it would be pretty useful.
Say
Yes.
that one more time.
This particular program, the Sage server, the file sageserver.py that implements the server, it imports the Sage library. The Sage library is GPL'd, therefore this program itself,
Has to be
the specific program that's running that imports has to be GPL'd if I redistribute it, which I'm not actually doing right now, but if I were to start like selling Salvus, for example, like the source distribution of Salvus that I've written to a company, then I would be distributing Salvus. And at that point, any code in there that derives from GPL code would have to be GPL'd and hence open sourced. So, of course, I want to open source it anyways, because I think it would be a nice thing to have in Sage, where you could just start up a little Sage server on some TCP port and connect to it. And then you can send messages using protobuf and get back results. And it's a very solid, robust binary format, so it's pretty useful.
But you don't have to worry about GPL stuff if you say sell some company Salvus and it says, oh hey, call this other.
Right, because that's just connecting to a different program over a network connection. That's allowed. you can't link in a program in this. You can't have one single program that links in a GPL library.
Without GPL.
Yeah, without GPL in that program. But you can have, just like I can link in, I can connect to Mathematica from Sage without violating any licenses. Two programs can communicate over the network, and there's no virality of the GPL there. So, let's see. And I just showed you this, so I don't need to say any more about that. Service management, I pretty much showed you that earlier in the talk, but this is some of the history of what happened. I actually wrote a bunch of code where I made a Tornado-based web server for managing infrastructure. So I had a nice little graphical interface and had a list of the virtual machines, and you could start things up and stop them. And I started realizing I was doing a lot of GUI work and JavaScript work, but all the actual real hard work of managing infrastructure wasn't getting done at all. And it was really I don't know, it was going to take me forever to get the GUI to look just right, and it would still be incapable of doing anything cleanly. So I ended up stopping working on that, and now I just have a really good Python library that really does what I want, but I have to use it from the command line. And later I will write a GUI that makes it easier to see what processes are running, what their status is, and so on. I don't think that will be difficult at all, because now I know exactly what data I have. I know what information I want to model and so on. Also, so configuration management, there's probably like 50 programs for doing this. Wikipedia has a list of about 50 configuration management programs. The idea there is imagine you have 50 different virtual machines running, and you want to decide what programs to run on them, and you want to start them automatically and stop them automatically and so on. It's a standard problem, and you don't want to be literally running around SSHing into all these machines and logging out and so on, because that just gets really tedious. So there's a bunch of people that have tried to solve that problem in various ways as part of they work at their companies or whatever, and they open source the result. So I looked at a lot of them. I found one I liked, but it turned out that it wasn't really that good, for what I needed at least. But there was something good about it, and it was this library called Paramico that's included inside of it, which I mentioned last time. So then I wrote something based on the same library, which is what I was showing you. And it's pretty short. Okay, and whoops. Summary, so it talks over. So here are the kind of axioms for the design of Salvus. So in any decision about what components to use and how to put the system together, no single points of failure. If there's a single point of failure in any design choice, then that design choice is just declared wrong, and I will not do it. Even if there's some sort of automatic failover, I don't want to deal with that because I don't have an operations team and it's too much work and too hard to get right. So I'm just not doing that. Interestingly, a lot of the Google technologies or things that I looked at that Google had open sourced often had single points of failure with a failover system. And I think that's the sort of thing that it makes sense if you have a large number of employees that can manage it. But I don't want to have to rely on that sort of thing. Everything as much as possible should be event-driven. So you saw that many times in the talk. Completely get away from polling and use WebSockets. But at every level, make things event-driven as much as possible. Have lots of separate, independent, clearly defined services. So for example, the static HTML gets served by Nginx. This makes it easy if I decide to instead serve the static HTML using a content delivery network or something else, because it's really sandboxed. It's just this one program that's serving on a certain port serves the static HTML. If I want to change, I don't have to rewrite things. I just write a different service that sits in its place. With the Sage Notebook, on the other hand, it's all tangled up in one massive single program. So changing anything involves weird repercussions between them, and it's really hard to understand what the interfaces are. So lots of services, or at least a couple of scalable independent services. Something I didn't say much about, but I spent a lot of time trying to make my code really short, just because it's a lot easier to manage and maintain. And often just spending a lot more time reading about what's out there can make code shorter. And I'm also pretty obsessed with making the month-to-month costs to run Salvus really low. Okay, that concludes this talk.